Hello everybody, welcome, thank you for joining us today. You are part of the 250 people worldwide who have registered to view this webcast, powered by Yole Development and sponsored by IQE. This webcast will be dedicated to gallium arsenide wafer and Epiwafer markets. My name is Faisal El-Kamasi. I'm Global Sales Support Coordinator for Yole Development. Before we get started with the webcast, I would like to give some practical information. You have the possibility during all the webcast to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as we can, and for the remaining question, we will make a following up via mail within a week. Concerning the materials and contents, please note that the presentation is available and downloadable in the resource section. You will also receive an email after the webcast with a link to the recorded session. Let's start the webcast with SD Douglas, Technology and Market Analyst for Compound Semiconductor and Emerging Materials in the Power and Wireless Division of Yole Development. SG, please.
Thank you for the nice introduction, Faisal, and good morning and good afternoon, everybody. So welcome to our Yole webcast on gallium arsenide wafer and Epiwafer market. And it's a pleasure for me to co-animate this webcast with Mr. Andrew Nelson, President and CEO of IQE. So let me first start my talk with a brief introduction on, it's not here, it's here, okay. So let me first start my talk with a brief introduction of our unit in charge of compound semiconductor activity at Yole. I think most of you are familiar with our company. So we are a market research and consulting company covering many fields from the industry, from photonics, sensors, power to RF and LED. And as you know, all these fields have significant drivers such as the 3D sensing, the upcoming 5G network, the hybrid electric vehicles, and many others. So at this point, it's quite important to note that at the core of all these technologies, compound semiconductors hold a key position. And for us, it's important to investigate the market and technology status, the challenges, the ecosystem, and of course, the future evolution of these semiconductors. So which materials do I speak of? So as a more than more company at Yole, we cover various semiconductor markets, the 3-5 group semiconductors such as the gallium arsenide and indium phosphide, the emerging wide bandgap semiconductors such as silicon carbide and gallium nitride, which we have followed from the early stages. And we also identify and cover emerging materials which we believe can have a great potential. And for example, this would be the gallium oxide, bulk gallium nitride, diamond, and many other materials. So we analyze the value chain from substrate to epitaxy for numerous end applications. So today's webcast will focus on gallium arsenide, as we have said, and I will refer as GaAs from now on for gallium arsenide. So now let's have a look at the brief history of GaAs, which is one of the oldest and the most mature semiconductor in the history. So it's already in 60s and 70s that we see the first demonstration of GaAs-based LEDs and solar cells, as you see here. And then we see the GaAs-based transistors being developed and revealing quite nice electronic performances, which made GaAs of great interest actually for power amplifiers, particularly in the handset applications. And then starting from 90s, we can say that GaAs wafer market found its first killer application in high volume consumer handset market with its deployment in the handset PA, the power amplifier. And this triggered actually development of larger substrates up to 6-inch, which is today the mainstream size for RF applications. And we also see demonstration of 8-inch wafers already in the early 2000s. And in parallel, we also see GaAs deployment in the photonics field. So we see GaAs laser diodes, which were started to be used in the data centers for short distance communications. And finally, last but not least, in 2017, we have seen that GaAs-based VCSELs, the vertical cavity surface emitting lasers, were started to be adopted for the 3D sensing applications in the iPhoneX, so which opened actually the door for full of opportunities for the GaAs market. And we can say that this will be the entering of GaAs again in a high volume consumer smartphone market. So this is an event which has significantly changed the GaAs market dynamics, to which I will address in the next slide. But we will also discover that the GaAs wafer market is also being driven by other emerging applications. So speaking of the applications, here you see the 4 big applicator markets which deploy GaAs wafers owing to their electronic and also optoelectronic properties. And these are RF, LEDs, photonics, and also photovoltaics. So we see that the RF applications use semi-insulating wafers which are not doped. On the other hand, the optoelectronic applications such as the LEDs, photonics, and photovoltaics, they deploy semiconductor wafers which are doped by zinc or silicon or during the single crystal growth of gallium arsenide. And regarding the applicator markets, I'll go into more details for RF, LEDs, and photonics. But a quick word on the GaAs PV market, the photovoltaic market. We can say that this one is each one compared to the others. But actually, the GaAs material system is very interesting for high efficiency PV systems under high sunlight concentration. But in the past, it faced some serious price competition with the conventional silicon-based solar cells, so it's limited its market growth. And today, we see GaAs being used in the space solar panels or on some high-end, lightweight, flexible systems, which represent a niche and stable growth market. And now let's go deeper with the applicator markets, starting with the RF. So we can say that in 2017, the RF GaAs market represented at least half of the global GaAs wafer demand. So with its high electron mobility and high power density, the GaAs-based wafers are mainly used in the PA, in the power amplifier, in the mobile handset, in wireless network applications, and RF power applications. But we can say that the main market for GaAs in the RF industry is really the PA handset. However, we see that the market growth for GaAs handset PA has slowed down in the past years, and we think that this is related to 2 main reasons. First is that the global handset market has also gradually saturated through the years, and secondly, we understand that there is still some room for die size shrinkage of GaAs HBTs, so the heterojunction bipolar transistors, which are used for these power amplifiers. And with the transition to 5G, we expect that the GaAs will remain one of the mainstream technology for sub-6 GHz PA, as high power and high linearity performances are still needed. So regarding the WLAN technology or Wi-Fi, as many of you would know, GaAs is still likely to be the still dominating choice for high power PAs, so which are of course required for high coverage of networks. And for the RF power applications, we see a rough competition between the GaAs and the emerging wide bandgap material gallium nitride for the PA technology. So we see that the GaN is offering high power efficiency with much smaller sizes, but on the other hand, the gallium arsenide proposes still cost-efficient and high-performance solutions. And GaAs substrates are also used for switch applications, which are still used for applications requiring high power, let's say, but they face tough competition with the SOI platform in the consumer handset market. And now let's go on with another big applicative market using the GaAs substrates, the LEDs. So the material system of aluminum, gallium, indium phosphide, which is epitaxially grown on GaAs substrate, actually they offer high brightness light emission in the red, orange, yellow spectrum, as well as in a part of the infrared spectrum. It would be up to around 1000 nanometers. And today, the red, orange, yellow LEDs represent a big segment in the global LED market. and they are driven by the emerging markets, as you see here, such as the LED displays, the automotive lighting, and the horticultural lighting, which uses artificial lighting for the plant growth. And as the red, orange, yellow LED technology continues to improve in terms of performance and it becomes more cost efficient, we think that it will penetrate faster in the automotive and horticultural lighting, where we expect a strong growth within the next years. But we can say that one of the largest market opportunity for the GaAs LEDs is in the LED displays. So GaAs-based LEDs are really important building blocks of red, green, blue LED models, which are used in the display technology. And in the LED displays, we have red, green, and blue chips forming individual pixels with pitches typically ranging from 1 to 40 millimeter. And of course, with the need for higher resolution and higher quality, the display systems, one of the main technological trends is to go to fine pitch systems. So this would be possible by gradually decreasing the pitch, which will result in an increase of the pixel density. So the number of the red, green, blue LEDs per surface would increase, and this would represent, of course, a significant demand of the GaAs substrate. So today, the fine pitch displays are emerging in the indoor applications, such as in the stores, in the shopping malls, or in the control rooms, and also in outdoor segments, such as in the stadiums or the billboards. But as I've said earlier, GaAs material system doesn't only emit in the visible spectrum, but also in the infrared spectrum. So, for example, around 940 nanometer, we see GaAs-based infrared LEDs used for proximity sensors and eye tracking systems in the smartphone. And other emerging markets would be the automotive and augmented reality and virtual reality, where infrared LEDs are used for eye tracking and gesture recognition. But we also expect a strong growth for GaAs wafer for medical applications, such as in the blood pressure sensors or the blood sugar monitors, as well as in the gas sensors for the security applications. So we can say that in many of these infrared and LED applications, we see a competition with the gas-based laser diodes, which can also offer a coherent beam with resolution and less power loss. On the other hand, the infrared LEDs still offer cost-efficient solutions. So this would bring me to my final GaAs application, which is the photonics. So historically, the GaAs VCSELs and the edge-emitting lasers emitting in the infrared were used for datacom and some legacy applications, such as the optical mice or the laser CDs. And these markets, you can say that they represent a niche market with steady growth. But with the introduction of the iPhoneX, using the GaAs VCSELs for the 3D sensing in the smartphone, and also the 3D sensing application of LiDAR, which is quite an emerging market, we expect great market opportunities for GaAs photonic applications. So I will go in more detail in the next slide. And finally, last but not least, we also see GaAs VCSELs, which are entering the industrial applications, such as the industrial heating systems and machine systems, which show good growth potential. Now, let's come back to the 3D sensing for facial recognition in smartphone, where a real market boost is happening since the Apple leads its iPhoneX with the GaAs VCSELs. So here we see the technology of Apple in the iPhoneX for the 3D sensing on side. So where you see 3 different GaAs VCSELs are implemented. So the first one is in the proximity sensor. The second VCSEL would be in the flood illuminator, and the last one is in the dot projector module. Actually, these VCSELs are quite different in output, the die size, number of cavities, and also the manufacturing. And here I can say that for more details on device manufacturing and VCSEL technology, I invite you to watch our webcast on 3D sensing and also VCSEL technology done by my colleagues quite recently, that you will find on our website. But for us, from wafer and epi-wafer point of view, it's important to note that the adoption of GaAs VCSELs in a high volume market has some big consequences at the wafer and epi-wafer level. So today we see a transition from the mainstream 4-inch GaAs wafers for the photonics to 6-inch GaAs wafers for cost-efficient 3D sensing VCSEL fabrication. And this transition brings, of course, technical challenges and new specification requirements which wafer and epi-wafer suppliers have started adopting. And it's important to note that these VCSEL structures are quite different from the ones that are used for the datacom applications, with more complex and challenging structures. Just to give an example, you can go up to 400 different layers, for example, epitaxy layers with different doping and composition profiles. And we should say that this emerging market is continuing to grow since 2017. For example, Apple has renewed its choice of integration of GaAs VCSELs in its latest models in last September. And we also see the competitors, Xiaomi and Oppo, who have presented also their latest brands with GaAs-based 3D sensing VCSELs. And we expect that the other Android platforms are also going to adapt GaAs VCSEL technology in the near future. But however, we consider that the 3D sensing VCSEL market is not the only booming market for GaAs substrate. So another emerging market where the GaAs-based laser diodes, or more particularly the age-emitting lasers, are used would be in the LEDs. So, in the LiDARs. So LiDAR applications enable creation of 3D mapping, and it's a high-end technology actually using time-of-flight principle, and it's expected to grow rapidly in various emerging markets, such as I have listed here, such as in robotics and surveying geosystems or robotized vehicles and in autonomous vehicles in the long term. And here, since high power detection is the key parameter for the LiDAR technology, we expect a significant use of GaAs age-emitting laser arrays, and of course a high demand of GaAs wafers in the next 2 to 3 years. So it's quite important to keep an eye on the LiDAR application, which is an emerging market, which can significantly change the GaAs wafer market again. So in this context, if we sum up and have a look at the market forecast, you will see that in orange, the GaAs wafer volume for photonics is expected to grow by a factor of 5 in the next 5 years. So this would be, of course, owing to the rapidly growing market of 3D sensing for high-volume smartphones and also the emerging LiDAR technology using GaAs-based lasers. And regarding the LEDs that you see in the green bubble, which represent the second biggest market in 2017, we think that the substrate volume is going to triple by 2023, and it will be mainly due to the emerging red LED demand for the high-resolution fine-pitch LED displays. And for the RF market, which is being gradually saturated, let's say, we expect a steady growth, but of course it will stay as one of the largest markets for GaAs. And now let's have a look at the industrial aspects of GaAs wafer and epi-wafer markets. So for the wafer supply, we see 3 leading players, Mitomo Electric, Freiberger Compound Materials, and AXP, having large market shares, and we expect them to keep their leading positions in the upcoming years with their technical experience. And then for the GaAs epi business, we see business models and epi outsourcing are really market dependent. For example, for the LEDs and the PV industries, they consist of rather vertically integrated device manufacturers, while the RF and new photonic applications such as 3D sensing VCSELs, the epi outsourcing is very high. So for RF, where the mainstream wafer size is 6-inch, due to specifications in the PA handset, for example, we have always seen a high epi outsourcing from well-established epi houses such as IQE. VPEC, and Sumitomo Chemical, and Intel Epi. And for photonic markets, which is historically driven by the datacom, the business models were dominated by the IDMs. But with the new 3D sensing VCSEL on 6-inch wafers, we expect to see a very high outsourcing of the epi wafers. For example, in 2017, Apple supplier Lumentum significantly outsourced its epi wafer IQE. And I think in this context, Mr. Nelson will also address this point in his talk. But we can also say that in parallel, since last year, we have seen many investments from the epi houses and also the LED manufacturers to enter the VCSEL business in order to benefit, of course, from this huge opportunity of high volume consumer market. So now let me summarize my talk with these graphics. So we can conclude that during a long time, since the beginning of the 2000s, the RF industry dominated the GaAs wafer market. And now with the changing market dynamics, with the emerging LED displays and also the entry of 3D sensing GaAs VCSELs in the high volume smartphone market, we expect the market size to double within the 5 next years. So we can say that by 2023, we think that the GaAs, optoelectronics, and RF markets are likely to coexist. And then in long term, with the potential boost in the LiDAR market, we expect GaAs optoelectronic markets to dominate the global GaAs industry. So that would be all from my side. So I thank you for your attention, and please don't hesitate to contact us, Hong Lin, a senior market analyst, and myself, if you have any questions on GaAs or any other compound semiconductor material that I have presented earlier. And this report on gallium arsenide, of course, it focused more on the substrate and the epi wafer. It was prepared by our unit, some compound semiconductor unit, but with the help of the related end application report that you see here from Yole Developments, and also with the help of the reverse engineering done by our sister company, System Plus Consulting. So thank you.
Thank you very much, Ezgi, for your relevant presentation. Once again, do not hesitate to ask questions using the Q&A button for the Q&A session at the end of the webcast. Now let's continue the webcast with a presentation by Drew Nelson, CEO of IQE. Please, Drew, the floor is yours.
Okay, thank you, Phailan. Thank you, Ezgi. Good morning, good afternoon, good evening for all the listeners around the world. My name is Drew Nelson. I'm Chief Exec of IQE PLC. And today I'd like to give you an introduction to IQE and focusing particularly on the gallium arsenide side of our business, but also give you an overview of a cluster that is formed in the UK called CS Connect, where we have an end-to-end ecosystem delivering on compound semi applications. So first of all, let me introduce IQE and its vision and mission. First of all, our vision is to be the #1 global provider of advanced semiconductor materials technology solutions. And our mission is to use our technology leadership, scale, to deliver to our customers the performance, the cost points, the security of supply, and strategic roadmap to enable the mass market adoption of compound semiconductor solutions. So here's a thumbnail of IQE. We are global leaders in compound semiconductor wafer technologies, founded in 1988, so we're just over 30 years old. We celebrated our 30-year anniversary last year. We're listed on the London Stock Exchange in the UK with a market cap approaching $1 billion US. Global facilities, as you can see from the map, with facilities in the USA. We have facilities on the eastern seaboard and on the western seaboard. We have facilities in Europe, particularly in the UK, and we have 2 facilities in Asia, in Taiwan and in Singapore. We employ about 600 staff globally, and we serve many different end markets, as you can see from the right-hand part of the slide, right the way through from communications to aerospace to security to healthcare. The next slide illustrates essentially our overall business. We are the global leading materials solutions provider for advanced and next generation semiconductor technologies. And what we have to offer as unique selling points are our breadth of product range, economies of scale, unrivaled product and service quality, integrity and confidentiality in our business models, technology leadership, and intellectual property that we've been developing over many years. On the left-hand side, you can see the inputs, in other words, the customers. Traditionally, our customers have provided detailed technical specifications, and we share business plans and product forecasts. But more recently, as we've expanded our technology platforms in many areas, we're building very powerful strategic partnerships with our customer base. Clearly, we rely on very skilled, world-class technical people in our organization who provide our customers with a friendly and constructive business, employing ethical business practices. Our equipment is high specification, state-of-the-art capital equipment, particularly MOCVD, MBE, and CVD, which we modify ourselves for our own requirements. And finally, our materials, our raw materials include the substrates, silicon, gallium arsenide, indium phosphide, and silicon carbide, gases and metal organics, which are provided by trusted and high-quality supply partnerships. We serve the market on the right-hand side through principally three business units: IQE Wireless, which serves the wireless market, RF power amplifiers, and switches. We're now introducing RF filters to the marketplace based on a unique technology based on rare earth oxides. Our Photonics division delivers VCSELs, edge-emitting lasers, DFBs, and photodiode sensors. And then we have an infrared division, which is the leading company around the world in providing gallium antimonide and indium antimonide substrates and epiwafers. They also provide quantum cascade lasers and a variety of different sensors. Complementing that, we have a range of emerging technologies, including nano-imprint lithography, which I'll touch upon later, quasi-photonic crystals, crystalline rare earth oxide. We have solar technologies, GaN power technologies, and finally, we focus a lot of effort on 3-5 on silicon integration. And these markets that we serve and are differentiated from silicon principally by the great technology leadership of compound semiconductors in the fields of speed, in light, and in power. So these translate very much into the macro trends which are driving both current opportunities and tomorrow's opportunities. So speed in terms of connectivity, light in terms of sensing, and power in terms of energy. You can see today's drivers include 4G, LTE evolution, massive MIMO, fiber backhaul, and then in sensing we have 3D proximity and time-of-flight sensing that Ezgi just touched upon, and energy, electrification of vehicles, big data, and solar-powered UAVs. And I think we're all very well aware of the very strong drivers for tomorrow's opportunities, including 5G, autonomous vehicles, virtual and augmented reality, wearables, chemical and biological threat detection, and high-altitude pseudo-satellites. So there's a huge opportunity for compound semiconductors moving into the future, and we are delivering products and designing products that enable these marketplaces. The evolution of our business model, and forgive me for the animation, it's not working quite as we expected, but what we're doing in terms of evolution of our business model is moving from just the materials foundry serving epiwafers, where the specifications are provided by our customers and led by chip design, to IQE providing a broad range of material solutions to enable our customers to develop innovative and disruptive products for the marketplace and enable us to support them in significantly more ways than just their epiwafer requirements. So you can see from the hexagons on the right-hand part of this slide a number of technologies, including nano-imprint lithography, quasi-photonic crystals, rare earth oxides, wafer bonding, epi-metal, and other technologies, which allow us to provide a broad range of additive technologies and complementary technologies to our epiwafer services. And you can see from the different parts of our business where these technologies will impact as we go through time in terms of introduction of new technologies to the marketplace. So let me illustrate that by looking first of all at the wireless marketplace. Wireless, as you know, is moving towards 5G, but 5G will not just be the next G. We think it will have many very powerful use cases, including fixed wireless access, Internet of Things, augmented and virtual reality, enhanced mobile broadband, and obviously for things like autonomous drive vehicles, ultra reliable and low latency communications is an absolute must. The key technologies that are required for this include high frequency, small cell, beamforming, and full duplex. And so if we look at what the network evolution might look like in this, there'll be the traditional base stations, which provide the infrastructure. There'll be the handsets, and then closer to the user will be 5G millimeter wave delivery systems. And if you look at the materials that are likely to be used involving compound semiconductors in different parts of the network, then in the infrastructure, gallium nitride is beginning to take a very significant portion of the marketplace as power demands are required, high power demands and high efficiency are required. The handset traditionally uses gallium arsenide for the power amplifier and the low noise amplifier, but increasingly there will be big demands on higher efficiency power amplifiers, on the RF filters, and on the switches required for these advanced handsets. And then in the 5G millimeter space, there will be new products required, particularly gallium nitride power amplifiers and GaAs reactors, to enable the directionality and high frequency operation of these systems. Where IQE is setting its product range out is not only do we have advanced HBTs and BiFETs and BiHEMTs power amplifiers for the handset market, and on the left you can see our solution includes a base layer of very high quality dilute nitrides, which will enable much higher power added efficiency. But in the switch field, not only do we have gallium arsenide PM technology, but we also have a technology called porous silicon, which we're bringing to market, which is very complementary to SOI. We are using our traditional GaAs PHEMT and GaAs HEMTs for the millimeter wave markets and for low noise amplifier markets. But very critically, we're also bringing to market a rare earth oxide enabled filter, high frequency filters for both bulk acoustic wave and surface acoustic wave filter technology. This is a very unique solution, which we think will be able to provide very high quality and high frequency filter operation. And these are generally 2019 new product introductions for the company. If we move to the photonics field, IQE has a very broad range of photonics products, from emitters to detectors, and you can see on the left-hand side of the chart many different kinds of emitters, from VCSELs through to edge emitters. And on the detectors, we cover wavelengths from short wavelengths right through to very long wavelengths using our antimony-based product solutions. Here we see the two major products that we serve the emitting market with. Our gallium arsenide products range from 3-inch right up to 6-inch at the current time. Our indium phosphide products, generally 3-inch and 4-inch, although we're working on 6-inch as well. And in gallium antimony, which serve the infrared part of the marketplace, then we go right up to 6-inch, both substrates and epiwafers. And the VCSEL development that we've done and the ramp translates very much to enhanced capabilities applicable to the edge emitting laser market, because VCSELs are critically dependent upon uniformity, thickness, and doping control, which are very sensitive in that device. So moving to edge emitting lasers, we've developed a technology called nano-imprint lithography, which is highly appropriate to large area production of distributed feedback lasers. It involves using a mold which is created by e-beam lithography, so very precise. We then use a proprietary technology for imprinting and removing the mold, and this leads to very high quality, high fidelity gratings for distributed feedback lasers, which we are now bringing to market as a full service manufacturing solution. In terms of VCSELs, as I think all of you are aware, the VCSEL is an extraordinarily difficult device to manufacture in a large volume across large areas, principally because the demands of wavelength control require extreme thickness control, doping control, and compositional control across the entire area of a 4-inch wafer or a 6-inch wafer. We were the first to market with commercial 150 millimeter products, and we believe we command around 90% of the market share for outsourced VCSELs right now. And you can see that we have a very long history in VCSEL manufacture going right back to 1994 when the first 4-inch VCSEL demo was demonstrated by the company. Currently, we are bringing into manufacture a Newport facility, which has a very large capacity ultimately for something like 100 epi tools. We are bringing online the first 4, the first 5 of which are now into qualification and production. And the VCSEL applications, as Ezgi mentioned, are much more than just 3D sensing, including LiDAR, data centers, industrial heating, machine vision, printing, and even cosmetics. So we have very large markets to aim for with our latest VCSEL technology. Now, as part of our future roadmap, IQE is bringing to the market some very unique technologies. First of all, not only will we not stop at 150 millimeters, we believe we can get to 200 millimeters as a demonstration towards the end of this calendar year, and even move towards 300 millimeter implementation in 3 or 4 years' time. We are developing longer wavelength VCSELs to address potential eye safety concerns. And in terms of integration, the form factor we can see changing from what it is today by including things like silicon photonics, wafer level optics, which are manufactured by nano-imprint lithography and use quasi-photonic crystal designs, diffractive optical elements, which do the same, and then even longer wavelength CMOS sensors. So you can see we have a very powerful roadmap, not just for the next 1 or 2 years, but stretching out over the next 5 or 6 years. So to address and support these various roadmaps, we have a very strong emerging technologies relevant to gallium arsenide applications. I'll quickly run through these. First of all, we have the rare earth technology, which we see as a very strong enabling technology platform across multiple markets. So if we look at the ability for Creo to provide a platform for integration of gallium nitride with silicon, then we can produce non-polar nitrides. This leads to group 3 nitride photonics for gallium nitride power and for gallium nitride and RF. If we look at the ability for Creo to enable platforms such as high-quality aluminum nitride, then this leads us to very high-performance filters. We are able to provide a material also based on rare earth oxides called rare earth pnictides, which incorporate a group 5 rather than the oxide. This allows and facilitates silicon photonics platforms. And then it also allows compound semiconductors to be produced on silicon substrates, addressing the current gallium arsenide markets. So you can see this is a very, very powerful technology for future applications. In terms of dilute nitrides, which are based on gallium arsenide substrates, the applications here include HBTs, high-efficiency HBTs, long wavelength PIN and APD for sensors, and long wavelength VCSELs. And here's a couple of illustrations of that. So, for example, to make a higher power added efficiency HBT, what we've introduced is dilute nitride materials into the base of a conventional gallium arsenide HBT, and we can get significantly better power added efficiency through energy gap reduction. In the case of photodetectors, typically communication photodetectors are produced on indium phosphide substrates, which are very expensive, typically limited to 4-inch wafer size. We've been able to develop a technology based on gallium arsenide substrates, which clearly lead to lower cost, easily scalable, even to 8-inch, and tunable for the range of 1.3 to 2 microns. So that's another product we're bringing to market this year. And then finally, we have dilute nitrides for longer wavelength VCSELs. We've already demonstrated using these technologies a wavelength emission of 1.3 microns for longer wavelength VCSEL applications. And finally, the filter opportunity, you can see the traditional offering is using sputtered technologies. IQE is offering an epi solution which allows Creo to be the platform for epi metals and epi aluminium scandium nitride, leading to much higher quality filter technology than is currently available in the marketplace. Finally, let me talk about quasi-photonic crystals. Many of you would not have heard of these, but essentially they are patterns of holes and shapes that one can drill into materials, various materials, which allow very effective manipulation of light signals for various applications. So let me illustrate what that can be used for. As you probably know, in any teardown of a 3D sensing unit, you see a very complicated optical package that takes the VCSEL array and, first of all, collimates the light beam and then replicates it through a diffractive optical element. We believe quasi-photonic crystals can be used to affect the same kind of output. And here's an example on the right-hand side of how various quasi-photonic crystal structures can be used to manipulate light signals in many different ways. So we are currently working on a wafer-level optic manifestation of which, where we think we'll be able to integrate a wafer-level optic within a VCSEL structure, and so collapse both the form factor and the cost of these optical systems used in 3D sensing. So in terms of our global manufacturing strategy, as I mentioned earlier, we have operations spanning the 3 different continents. On the right-hand side, you can see the different application areas of each of our different operations around the world. And these are designed to provide geographically separated internal second source for many of our customers and many of our products. So in disaster scenario planning, we can effectively guarantee our customers supply from different parts of the world. Our latest rather large investment is in our Newport Epifoundry. This is a very large facility capable of taking about 100 epi tools. Now in full operation, we have 5 tools now production ready and customer sampling and process ready. By the end of the first half of 2019, that will rise to 10, and we'll have 20 reactor bays ready for occupation beyond that. So let me move on to, in the interest of time, to talk a little bit about the ecosystem that surrounds that mega facility. What we've created in South Wales in the UK is an end-to-end chain, and the manifestation and the drive for this was recognizing what Ezgi said a little bit earlier, that compound semiconductors really at the heart of many of the innovations around the world today and systems today. What we're trying to create is end-to-end supply systems and supply chains based on compound semiconductors and compound semiconductors integrated with silicon. So if you look at this chart here, basically you can see that compound semis and silicon as semiconductor materials are absolutely at the heart of all major industrial areas today, whether it's communications or healthcare or automotive or aerospace. Then compound semiconductors are very much at the heart of these supply chains as critical components. And clearly, as you go through these supply chains, then the economic value increases pretty significantly. So what we've done is we've created a chain of institutions and companies which cover the entire technology readiness level scale, but also cover the operations from wafer manufacturing right through to packaging, through the equipment side of things with SPTS, chip manufacturing via Newport Wafer Fab, and packaging through Microsemi. The UK government has recognized the importance of compound semis as a fundamental enabling technology. They're investing significantly into what's called a catapult, which is a center which does interacts closely with industry and develops innovative solutions to their problems using the compound semiconductor ecosystem that have been developed in South Wales. So you can see here the various institutions that are involved, from the Institute for Compound Semiconductors at Cardiff, the Compound Integrated Semiconductor Materials Center in Swansea. IQE has a Compound Semiconductor Center joint venture with Cardiff University. And then you can see the entities for full manufacture: IQE, SPTS, Newport Wafer Fab, and Microsemi, supported by Cardiff City Region deal, which you can see here is allocated a very significant amount of money to the innovation system surrounding the Cardiff City region. So here are the entities in the core of the technology platforms, and here are the various companies in the region who are part of the overall ecosystem that is now developing supply chains in advanced compound semiconductor technologies. Cardiff University is one of the founding members of the cluster. It's focusing on a range of different technologies and is building a new clean room which will take up to 8-inch wafers. So it's operating very much along industrial lines as compared to traditional university type environments, so that products can be rapidly taken through from early stage TRL levels right through to mass production. It encompasses the Future Compound Semiconductor Manufacturing Hub, which is being sponsored by the EPSRC, which is a core funding body within the UK for advanced technologies. In terms of integrative semiconductor materials, this has been done at Swansea, where they're taking next generation materials and processes, integrating them with next generation compound semiconductors to provide advanced platforms for the future. This is IQE's Newport Mega Foundry for Epi. As you can see, it's a pretty sizable building. This is already now in full operation and eventually will take up to 100 tools. Newport Wafer Fab is the UK's largest 200mm chip manufacturing facility, located only about 5 miles from the Epi Foundry. This is the UK's #1 silicon chip plant, but is now being directed towards becoming the world's first compound semi on silicon chip plant. This is an overview of the site. The 8-inch fab is capable of between 8 and 10,000 8-inch wafers per week, so pretty high volume manufacturing. And by incorporating compound semiconductors into the silicon technology, then we foresee a great future for introducing higher levels of compound semiconductor into different applications. SPTS Technologies is a leading manufacturer in the gallium arsenide world for etch and deposition process solutions. It's a core member of the cluster, as is Microsemi, who are into very advanced packaging. They have introduced wafer scale module technology, which uses compound semiconductors, and that's being introduced with a number of their major customers. In terms of the cluster locations, this is about a 20-mile stretch of the M4 motorway, and you can see that all of the key companies are located within a very small geographical area, meaning that interaction between these companies and the ecosystem is very, very powerful, as is the interaction between all the people involved in the cluster. So, as you may know, in Europe, there are 4 major clusters in Grenoble, Leuven, Eindhoven, and Dresden, and the Cardiff region is now host to the next semiconductor cluster, but it's now focused very much on compound semiconductors, and we believe this is the world's first really end-to-end compound semiconductor cluster ecosystem. Economic benefits are a global compound semi-wafer and chip foundry as pivotal mass production entities, a European CS prototyping development center, the establishment of very powerful centers of academic excellence, providing the skill sets for the future workforce, formation of significant number of new SMEs, creation of between 2,500 and 5,000 high-value jobs, and the world's first compound semiconductor cluster. So I invite anybody out there who are interested in exploring what the ecosystem has to offer to get in touch. It's branded CS Connected. There's a website, csconnected.com. Please visit that, and if you have an interest, then please contact us. So with that, I'll hand you back to Pascal, and thank you very much for listening.
Thank you very much, Drew, for this very interesting presentation. Now it's time. We are now going to wrap up with a Q&A session. We will answer as many questions as time permits and follow up via email on the remaining questions. Let's start with the first question. This will be for you, Ezgi. What is your opinion about a potential transition to 8-inch GaAs wafers?
Yeah, it's a good question, actually. So, actually, historically, we have seen the wafer sizes for the LEDs, for example, the mainstream size 4-inch. For RF, it is around 6-inch. Now, with the transition to 3D sensing VCSELs, we also see a transition to 6-inch wafers. But to be honest, there's little amount of 8-inch wafers today in the market. And for example, for the RF applications at the foundry level, it's around 6-inch. So, but yeah, the 8-inch wafers actually they have been ready since quite a long time. So it's already in the beginning of 2000s that they were demonstrated by the leading substrate suppliers. So it has been quite a long time, but we haven't really seen utilization of 8-inch in the foundries, for example. And we understand that the feedback we have from the industry that, for example, for the VCSELs, the transition to 8-inch gallium arsenide wafers would be even more complicated than it is for the 6-inch. So on that side, we won't really see an imminent transition to 8-inch. But with the discussion with the industry, we see that one application which can maybe make a transition to 8-inch would be the micro LEDs. But here it's quite a disruptive technology. It's not like the fine pitch LED displays that I have presented. So it's a really new one. It's an emerging technology. Today there are many players positioning with many techniques, and the main technological trend is not to be, I think, doesn't seem to be defined yet. We see some prototypes, for example, from Samsung at the CES show. But yeah, as I said, it's quite early technology. So, and we will also see how it will impact the gallium arsenide. So maybe it's quite early to tell for the moment, but this can bring some market opportunities for the gallium arsenide 8-inch at some point. But for the micro LED technology, you can refer to the webcast from our colleague, senior analyst Eric Ray. He made a really good webcast on this. So for more technical details, please see this one.
Thank you, Ezgi. The next question will be for Drew. Drew, there was a lot of hype about 3D sensing last year, but adoption of the technology appears to have slowed. What do you think will drive the adoption of 3D?
I think it's only slowed because it's a product and a technology which has got a new introduction to consumer markets, and that's always, particularly if there's a single company who is leading the way, then it's always likely to, have a not perhaps a smooth transition. But I'm pretty certain that what will happen is we'll see mass adoption of 3D sensing across many ecosystems. Handsets is an obvious one. I think Ezgi already pointed out that a number of other handset makers are introducing 3D sensing into their platforms. But I think it's a little bit like when cameras were first introduced to smartphones. They were introduced at the high end. But today, you can't buy a phone which doesn't have a camera on it. So I think this exactly the same dynamic will happen with 3D sensing. There are so many powerful use cases, but it will also, I think, extend very rapidly into many of the areas that Ezgi touched on. Machine vision, LiDAR, all sorts of different applications in augmented reality and virtual reality. So I think it's a technology which will rapidly increase over the coming years, which is why IQE has a very strong roadmap for addressing the issues that we see coming into play.
Thank you, Drew. We have still time for maybe one or two questions here. Ezgi, what will be the impact of entry into smartphone mass market on the GaAs photonics, wafer and epiwafer industry?
Yeah, thank you for the question. I would say that historically, the gas photonic market, as I've shown in my presentation, is more vertically integrated, similar to the LEDs or the photovoltaics. But indeed, with the entry into a high-volume smartphone market, it's a consumer market, the business models will change actually. So we understand that from the feedback from the industry that the EPI for 3D sensing is quite challenging, and as Mr. Nelson has explained, it requires significant investment, know-how, and also development for qualification. So for the laser manufacturers, I think that it would be more flexible for them to outsource the EPI wafer and for the volume needs and also for the specifications. So yeah, to conclude, I would say that the photonic EPI wafer market maybe will behave more similar to the GaAs RF EPI wafer market, which is also a consumer market with high volume and high specifications requirements.
Okay, thank you, Esgi. This made clear. Let's do a last question for you, Drew. Will be, when do you expect new technologies such as the PQC to be commercially available?
I think they will be available. I mean, they're essentially available for simple applications today. But I think in the applications that I mentioned, in terms of wafer level optics, in diffusers, in distributed diffractive optical elements, I think you'll see these introduced in the next 12 to 18 months.
Okay, thank you very much, Drew. So we have other questions, but the time has run out. So the webcast is ending. We will try to answer the other question by email. So within the next 24 hours, you will receive an email that will include the link to the recorded session. Please feel free to share the presentation with your colleagues. Also, you can review all our analyses and report on our i-micronews.com website. Thank you for joining us today. Do not hesitate to contact us if you have additional questions. You can find your appropriate contact at the last slide of the presentation. Have a good day. Goodbye.